Hey guys, so this is the final one we're going to do. We're going to do exponential models. So just a quick thing. Linear models we saw in our previous lesson represented quantities that change at a constant rate. That is, like a fixed amount is added to the quantity at regular intervals. So I just want to make note of that it's added. But exponential models represent quantities that change at a constant percent rate. And that means the quantity is multiplied by the same amount. So linear is added by the same amount every time, and exponential models are multiplied by the same amount. Multiplied or divided, depends on how you look at it, but it's always like the same multiplication in this case. Let's look at some examples and it might make a little bit more sense. So we're going to recognize linear and exponential models in this example. Last year, a school population of 1,000 students, and this year, 1,100 students attended the school. So it's an increase of 100 students or 10%. We're going to first determine the population after 3 more years under each scenario. So they have scenario A, the population increases by 100 students per year. So if they're going to increase by 100 students per year, that means they're going to add. Oh, come on. Let's use the pen. They're going to add 100 each year. So right away, because there's addition, I think linear. And the second one, scenario B, the population increases by 10% each year. So that's a percentage. And when we're talking about percentage, we're going to multiply by 10% each year. So that one, because it like screams multiplication, means it's going to look more like an exponential model. What type of growth does each scenario illustrate? So I kind of already gave it away. But let's do the math behind it. So let's look at A. So we're going to add 100 each year. Okay, so we're going to start with 1,100 students. After 1 year, 2 year, 3 year. So after 1 year, we're going to add 100. So we're going to have 1,200. Year 2, we're going to add 100. So 1,300. And then year 3, we add another. So notice how this one goes up by the same amount every year. B, we're going to multiply by 10% each year. So we're going to start with 1,100. Then maybe 1, 2, and 3. So each year we're going to add 10%. So we're going to multiply and add 10%. So if I do 1,100, I'm going to multiply it by 10% and then add it. And I get 1,210. The next year I'll get 1,331. And then the following year I get 1,464.1. So all I did was multiply each year by 10% and add it on. So notice that one obviously does not go up by the same amount each year, like addition wise, but it is multiplied by the same thing each year. So that gives us to question B, which says, which type of growth does each scenario illustrate? This one was linear because it added the same amount per year. And this other one over here, it is exponential. And why? Because it multiplied by same amount each year. So if you want to sort of remember this one, you can be like linear addition, exponential multiplication. And that kind of helps you remember it. Exponential models, let's take a look down here. Exponential models have these characteristics. In a table of values, the growth factor or decay factor is equal. So it's the same thing. Basically, it's saying multiply same amount. Same amount each time. The graph resembles an exponential curve. Now, what does that really mean? Or you might be thinking, well, what does an exponential curve actually look like? It looks like this. It either starts off small and then goes up really fast, or it does the other thing and it starts off large and then comes down and slows. So both of those are exponential examples of exponential curves. The equation can be written in the form y equals a times b to the exponent x. A is the initial value, and b is the growth or decay factor. And I think if you took the grade 11 college course, then we went over this a couple times, and I might add a couple videos in here that I already have to kind of help with that. But if you have forgotten, you can take a peek at them. But this is really the formula we're looking for in terms of exponential functions or exponential models. If you think it's an exponential model, the exponent is where the variable is. So the x or whatever you have to find or is changing all the time, it's in that exponent position. Let's move to the second page because I have a couple more examples that might kind of clear it up. Oh, perfect. Look at this example. We're going to identify exponential models, and I'm going to show you how can we tell if they're exponential models. Same as we did in the last lessons. So we're going to do the table first. This time I'm not going to look at the first differences and the second differences. I'm going to look and see if there is some sort of growth or decay factor, and I'll show you how to do that. So here we've got 35, 25, 15, and 5. Now, in order to find out if there's a growth or decay factor, all we're going to do is take the one number and divide it by the previous. So I'm going to take this one and divide it by this one. So I'm going to do 25 divided by 35 to find out if there is. And this, I get 0.71. And then I'll do the same thing with these ones. So I'll do 15 divided by 25. And I'll do the same, 5 divided by 15. So take the one and divide by the other one. It really doesn't matter which way you do it. But you're going to find out really quickly. Either way, it should give you the same thing. So divided by 25. This gave me 0.6. 5 divided by 15 is 0.3. So because they're not the same, when we do this division or we find a growth or decay, possible growth or decay, when we do this division, this is not exponential because they'd have to be the same. Now, if you wanted to find out what it actually was, you could, since we know it's not exponential, we could go and find the first differences and the second differences and see if there's anything, if it's linear or quadratic. I mean, looking at it, it goes down by 10 every time. So right away, I can see that all those first differences are going to be 10. So I know that this one's linear and it's not exponential. So you could do that if you want to. I'm not going to do it right now. But there are questions where you might have to do all three. Find the first differences, find the second differences, and then find the exponential just to find out exactly what it is. Part B, we'll do the same thing. So 51.2, 64, 80, and 100. So we're going to do the same thing. I'm going to do 64 divided by 51.2. And I get 0.125. Same thing. We're going to do 80 divided by 64. I think I may have done the first one wrong. Huh. 64. Guys, I don't know what's wrong with me right now. 51.2 divided by 64. Oh, I see. I had it. You've got to make sure you're doing it in the same every single time. So actually, let's do this one the same. You take the bottom one and divide by the top one. So this one's going to be 64 divided by 51.2. Which is 1.25. So I did have that one wrong. And this one gave me 1.25. And if I do 100 divided by 80, I get 1.25. So notice they're all the same. Just make sure when you do these, you always take one of them and divide by the other one. So in this case, I took this number and divided by the one before it. Then I took that one, divided by the one before it. So same. So it is exponential. Sorry, I didn't mean to confuse you guys. I confused myself. Let's do C and D. These are the graphs. C, I look right away. It's a straight line. Linear. Come on. Can't fool us anymore. B, D, you notice it starts off small and then goes up, up, up really fast. It's not a parabola because it doesn't make a smiley or a frown. It's not a straight line. This one is exponential. E and F, we've got equations. So notice on E, it's y equals 10 times 2 to the x. That's A, B with an exponent of x. Looks just like what I said on the previous page. So it's exponential. Exponential. Sorry, guys. And then the last one, y equals, goodness, I lost my pen. But the last, I think my battery and my pen died. I'm sorry, guys. But the last one, just take a look at it. Y equals 10x squared. Notice how the x is not in that exponential position. This one actually looks more like a quadratic. So f is not exponential. It would be considered quadratic. Okay, I'm going to do the last example, but I have to pause and take a break because I need to do my pen. You guys didn't really need to know that, but I'll be right back. All right, so back to the last example, comparing pairs of exponential relations. So two colonies of bacteria start with 100 bacteria. The population of colony A doubles every hour, and the colony B triples every hour. So notice, graph the equations on the same screen. How do these graphs compare and explain? So I'm just going to look at it. This one, notice that it has a 2 there. And this one has a 3 there. This is the doubles. So anytime you see doubles, it's going to have a 2 there. And this is our initial. And same here. This is the initial value, and then it's got a 3 there because it triples. Graph the equations on the same screen. How do the graphs compare and explain? How would the graph for colony A change if there were 200 bacteria initially? So I'm not going to go graph it. You guys can graph it in Desmos if you want, but I will tell you what it's going to look like or what you'll see. So if you were to graph the first one, colony A, you're going to get, that starts here at 100. And so it starts there, it goes up kind of slow, and then it will take off. And then the colony B, so that's A. Colony B, again, it's going to start at 100. It's going to go up slowly, but eventually, because it triples, it's gonna take off even more. So that's colony B. So you'll notice that colony B will go up faster than colony A, but they start at the same spot. How would your graph for colony A change if it were 200 bacteria initially? So you can change that on Desmos, just change this 100 to a 200. And I'll do this in green, but it'll start up here at 200. And it will take the exact same shape. It will just start. It will start at a different spot. It will go up kind of the same. It will actually go faster because you started with 200. So eventually it will pick up a little bit more speed than A did. But it kind of has the general same shape. But that's how it's going to look. I just wanted to go over that with you. Feel free to try to put it in Desmos, but that's enough for this lesson because we're already past 15 minutes. So I'll see you guys later. Bye.